0 is equal to 2.5 times 10 to the minus 5. So I'm going to plug all that in. So what's the physical interpretation of this? This is sampling time. So I'm sampling at every 1.25 times 10 to the minus 5th seconds. That's seconds per sample. And 0, that's basically related to the power spectral density of the noise. So that basically gives you an indication of how strong your noise is. And this is the number of samples per bit. Okay, at this point, what is the duration of a bit? In other words, TB.
18 to 1.25.
It's so I have 1.25 times 10 to the minus 5th seconds per sample, 8 samples per bit, and I want seconds per bit, so I multiply 8 by 1.25. And that is, I selected this carefully so that this would actually be equal to 1 times 10 to the minus 4 seconds per bit. And what is the bit rate, bits per in bits per second?
1 into the power 4.
1 times 10 to the 4, it's 1 over this, so it's 1 times 10 to the 4, which is 10,000 bits per second. Okay, so that's the physical interpretation of these numbers. Substituting them into this expression, we have 1/2 C square root of 8 times 1.25 times 10 to the minus 5 divided by 2.5 times 10 to the minus 5. Okay, for one thing, that'll cancel with that. 1.25 is exactly half of 2.5, so that'll be, I can cancel that. This turns into 2, so I get data for 2, which is 1/2 ERF C of the square root of 4, which is 1/2 ERF C. I selected these numbers carefully so this would work out nice. 1/2 ERF C of 2, and nobody has their laptop open, but I plugged this into MATLAB earlier, and the answer we get is 2.34 times 10 to the minus 3. So the probability that any individual bit is in error is equal to 2.34 times 10 to the minus 3.
Do we have the RFC function in our, like usually it's on the calculator, right? Like in the exams, we can...
My calculator is pretty old, but it doesn't have it. I don't know about, if this came up on a test, I'd give a table or something.
Okay.
But it's definitely in MATLAB. So, let's think of a different kind of problem. What would you do if I said, okay, that's not really acceptable. What I really want is 1 times 10 to the minus 4 probability of error. So in order to do that, basically, now we're starting on this side, and we need to know what goes into that argument in order to make that happen. So in MATLAB, there is a function called ERF C inverse, and it's written like this. that would do, in order to do something like that, if I said probability of error has to be less than 10 to the minus 4, what do? You say, okay, 1/2 or C of root NBTS divided by N0 has to be less than or equal to, let's call it equal to, that's easiest, equals 10 to the minus 4. And let's say I give you an N0. N0 is usually not under your control. These are the parameters under your control, NB times TS. So what you would then do is you would say, okay, if I'll take this 2 to the other side. And then I take ERC inverse of both sides. Okay, ERC inverse cancels with ERC, and I get root NBTS for N0 is equal to ERC inverse 2 times 10 to the minus 4. Okay, let's think for a second about what I'm actually asking here. N0, that's a property of the universe. So that's given to you. That's the noise power spectral density in your specific receiver at the specific temperature at which you want to operate. So that's not under your control. What is under your control is NBTS. So that's the number of bits per sample times the sampling time. And that's something that you can control. You can adjust that in your receiver. But what is NBTS? Remember, NB is the number of samples per bit, and TS is seconds per sample. So this is actually equal to PB, the number of seconds per bit. So the interpretation here is that this is equal to, what you're really adjusting is TB, the time per bit. And the way it works is that if TB increases, then probability of error will go down. So if you need to satisfy a probability of error criterion and you don't, and you can't satisfy it with your current system, basically what you'll do is increase TB. But what's the interpretation there? If you're increasing TB, what happens to the bit rate? It goes down. So basically, communicating at very high bit rate requires you to tolerate higher probability of error, or do things to mitigate higher probability of error. Whereas communicating at lower bit rate leads to lower probability of error. So in other words, it's harder to communicate at high bit rate. Okay, let's look at another example. So I didn't work this out, so you could get some numbers on your own. But let me just remind you, ERC inverse is a defined function in MATLAB, so you can use that.